All right, this section 2-8, we're looking at synthetic division. So the last time, in the last lesson, we went through long division, but there is a process that you can use called synthetic division to divide out the polynomials that is less writing and maybe a little bit quicker as well. And so here's the pattern for it. So if you want to divide this polynomial by this, then here's the pattern that you want to use. So whatever the 0 is, you would put that number here, right? And drop this straight down. So these are the coefficients in descending order of power, right, that go here. Drop this straight down, multiply the k times the a here, right? Then combine those, then multiply again, goes here, combine those, multiply here again, combine those. All right? And if you end up, this part would be your remainder. So if you end up with a 0 here at the end, that means it divides evenly. And if you don't, then that would be your remainder. All right? That would be your remainder. And so these here would be the coefficients of the quotient. And of course, it would be to one less power than what you had here. So let's see. Okay, now here's the synthetic division actually does have some limitations, and it works only for divisors that are in this form, x minus k, right? And so it doesn't work like one that we had done from the last time with long division where we divided by a trinomial. Synthetic division can't handle that, right? So that algorithm only works for divisors that are in this particular form. So make sure you're aware of that. All right, now here's some things to keep in mind with as far as what synthetic division yields for you. All right, so the remainder obtained by the synthetic division gives you the following information. Okay, the remainder gives the value of f at k of x. In other words, so r is equal to f of k. So in other words, if you plug that factor in there, or I shouldn't say factor yet because we don't know it's a factor. If I plug k in there into the function, then it would give me the remainder. All right, so that's what that means. So if I plug k into the function, then f of k equals to what the remainder would be when you divide it out. So the remainder gives you the value of f of k. Now, if the remainder is 0, then we know that x minus k is a factor of this function. Because remember, if you plug in a value and the function value is 0, then that is a factor. That's a 0 or a root of the polynomial, and then so x minus k would be a factor. And also likewise, if r is equal to 0, then k comma 0 is an x-intercept of the graph. So again, how do we know if we have a 0? Well, if you divide it out evenly and the remainder is 0, then it is a factor. All right, so make sure that you're aware of that. Okay, let's try one. Let's see how it works. Okay, so it says use synthetic division to divide. So when you're using synthetic division, okay, it looks kind of like this. And so I'm going to divide this by x plus 3. So what I will do here is I'll put minus 3 here because the value of k goes here. And remember what the form is. The form is x minus k. So you got to change the sign of whatever's here. And of course, that's what you would do anyway to get the 0 or the root. All right? So I'd put negative 3 here. Then I would write out the coefficients in descending order of the variable here. So I would have 1. Now, just like with long division, if there's a term missing, you got to put a 0 in its place. So you got a 4th power. You don't have a 3rd power. It goes down to 2nd power. So I have 0 3rd power terms, right? Negative 10x squared, negative 2x, and 4 is my regular number. So make sure you put zeros in for placeholders to whatever power is missing in order to make sure it works correctly. All right, so now what do? I can drop this 1 straight down. Now, here's how synthetic division works. Negative 3 times 1, negative 3. And so now 0 minus 3 is negative 3. Negative 3 times negative 3 is positive 9. So again, we're adding here and we're multiplying here. So negative 10 plus 9, negative 1. Negative 1 times negative 3 is positive 3. Minus 2 is 1 times negative 3 is negative 3. And then plus 4 is 1. All right, so what do we notice here? We notice we do have a remainder, because whatever's here is your remainder. And so when we go to divide this out, then the quotient would be, and remember, these are now the coefficients of the polynomial. To 1 degree less is what the term will start with. So when I write out the answer, when I divide this by this, we'll get negative 3. Oh, wait a minute. Hold on a second. I'm looking in the wrong spot. It's down here. So I've got 1, right? So that's 1x to the third. Then I've got minus 3x squared minus x plus 1, and then here is my remainder of 1. So remember, that's plus 1 over x plus 3. And then there's your answer. Okay, next thing that we come to is what is known as the remainder theorem. And here's kind of what it states. Okay, it says if you've got a polynomial f of x and it's divided by x minus k, then the remainder r equals to f of k. So remember, if you divide it out and you've got a remainder, that's the value of the function when you plug in the k part of what you divided it by. And that's very similar to the statement that was made up here in the one of the reminders for using the synthetic division. Okay, so we kind of already stated that up here, but the remainder theorem just kind of gives you that information in a theorem. Okay, so again, if you're dividing by this, then the remainder r is equal to the value of the function at k. All right, so we kind of already discussed that. On the back side of it now, there is a problem using the remainder theorem, and it says use the remainder theorem to evaluate the following function, okay, at x equals 2. Use the remainder theorem to evaluate the following function at x equals 2. Well, if we wanted to evaluate it at x equals 2, then the old way is to plug negative 2 in here and see what we get. All right? But if we're using the remainder theorem to do it, we need to divide this out. Okay, we need to divide this out and then see what the remainder is. So we can do it with synthetic division. And a lot of making sense of this is making sure that you understand what the math speak is saying. So my function is x equals, or my value is x equals negative 2. So that would be the same as dividing by x plus 2. If my value of k is negative 2, that's like dividing by x plus 2. So what goes here? It would be negative 2. The sign's already changed from what the factor would be. All right, so let's write out the coefficients. 3, 8, 5, negative 7. 3, 8, 5, negative 7. All right, so let's just divide this out, see what we get. Drop my 3. 3 times negative 2 is negative 6. That's going to subtract off and make 2. Negative 2 times 2 is negative 4. Minus 5 is 1. Times negative 2 is negative 2. Minus 7 is negative 9. All right? So if we wanted to see what that is when we divide it out, we could. It didn't ask us for that, but since we've already divided it out, we might as well see what the quotient is. It's going to be 3x, remember, 1 less power, squared, plus, next coefficient is 2, 2x, and then plus 1. My remainder is negative 9, so that would be plus negative 9 over x plus 2. And really, technically, if you just wanted to write that as minus 9 over x plus 2, you could. All right, now, here's the deal. Okay, remember what the remainder theorem says. The remainder is the value of the function at this number. So remember what they ask us to evaluate the function at x equals negative 2? Well, guess what f of negative 2 is going to be equal to? Well, it's going to be equal to the remainder, which is negative 9. And we could verify that by plugging negative 2 in here, here, and here, and multiplying it out and adding it up, and you would see that when you plug in -2, you would get a -9. All right, so we did it this way instead of the plugging in ways because it asked us to use the remainder theorem. So whatever the remainder is, that is the value of the function at this value that you divided out by. All right, now what else have we got? Okay, now we're going to be looking at the factor theorem, and this one states that you can test whether a polynomial is going to be a factor at k. Okay, so if the result is 0, then x minus k is a factor. Okay, so here's the deal. A polynomial f of x has a factor x minus k if and only if f of k is 0. So you can kind of see how all these statements are tied in together. If we plug in k to the function and we get 0, then we know that x minus k is a factor. So really all of these statements and theorems that we're looking at here today are tied together. All right, so we can kind of see how they are sort of kind of saying the same thing. All right, and so what do we have here? Okay, it says show that these two are factors of this polynomial and then find the remaining factors. Show that these are factors of the polynomial and then find the remaining factors. Well, the first thing that we want to do is show that these two are factors. Well, how would we know if these two are factors? Well, based on the factor theorem, if I plug in 2 and get 0, then this is a factor. And if I plug in -3 to the function and get 0, then that would be a factor. All right, so in order to figure that out, I can divide those out with synthetic division and see if I get a 0 here for my remainder. If I get a 0, then I know the value of the function at that particular value is 0, and then that would force it to be a factor. So by synthetic division, I can show that these two are factors, and then I can use that to then answer the subsequent question, which is find the remaining factors. So we're going to divide them out first. So I'm going to draw out my synthetic division. And of course, if x minus 2, if we're trying to show that's a factor, then I'll put a +2 here. And in my function, I'm going to have 2, writing out the coefficients, 7, minus 4, minus 27, minus 18. And then, so now let's go ahead and divide this one out and see if it's a factor. So I'm going to drop my 2. 2 times 2 is 4, plus 7 is 11. 2 times 2 is 22. Minus 4 is 18. Times 2 is 36. Minus 27 is 9. Times 2 is 18. Minus 18 is 0. So now we have shown that this is a factor. Why? Because my remainder is 0. And remember, if the remainder is 0, then that means that f of 2 is 0. And if f of 2 is 0, then we know by the factor theorem that it's a factor. So really to show that it's a factor, we're using the factor theorem, and then we're also using the remainder theorem to show that, hey, if this divides evenly, then it must be a factor. All right? So that's how we're tying all of these statements together. All right, let's see if x plus 3 is a factor. We want to show that's a factor now. If it divides out evenly, then it is. Let's see. So when I take this and I go -3 here, let's write out the coefficients again here. We'll go 2, 11, 18, and 9. The 2 will drop. 2 times -3, -6. That'll subtract off and make 5 times -3 is -15. Plus 18 is 3. Times -3 is -9. And then guess what we've got here? We got 0. So now, since this is 0, we have shown that x plus 3 is a factor by the remainder theorem and the factor theorem. That now shows that this is also a factor. So these are two factors. But now, what about the remaining question? Okay, what about the next question? The next question is, find the remaining factors. All right, find the remaining factors. And so one thing that I kind of blew past that I didn't really show here is, why was I using 2, 11, 18, and 9? Well, this, okay, would be a factor of this dividing it out. And so if I'm already showing that these are factors, which I probably should have done there to make sure that it divides into this, then I took this and divided into the result, the quotient. And the reason why I divided the -3 into that is because if it's already partially factored out and I already know they're asking me for the remaining factors, instead of dividing by the original thing again, I took what was already divided out from the first factor and then divide the second factor into that again, because now that would give me another factor. And so let's take a look and see what we've got left now. So what we've got left from here is 2x squared plus 5x plus 3. All right, so that's what we get after I divide this by the other factor. And so again, let me just kind of stop and make sure I've fully explained what I've done here. When I divide this into this, it divides out to make this polynomial, right? And now, if this polynomial, if it divides into this, then it's also a factor of the original one. So by this x plus 3 dividing into the resulting polynomial here, we also ensure that it's a factor of the original function. So I'm still showing that it's a factor by showing that it divides evenly into the previous quotient. All right? So in other words, thinking about it in terms of regular numbers, if 2 divides into 8, right, then it also divides into every factor of 8, right? So if 4 times 2 equals to 8, then of course 2 is also going to divide into the, if it also divides into the factors, then it divides into 8, okay? So if 2 divides into 4, then it also divides into 8 because 4 is a factor of 8, all right? So if the -3 term here divides into this, then it also divides into the original function because this is a factor of the original function, is what I'm saying, all right? So, and the reason why I divided it into this, besides the original function, is I know the remaining question is saying find the remaining factors. So by doing that, I'm continuing to factor it down, and it's helping me to get to my final answer. So what have I got here? I've got this. If I can now break this down into a product of two binomials, which I can, let's see what we can do here. And that's probably not going to be x, that's going to be 2x because of this. So now I've got 2x times x, 2x squared. So all this is positive, so I can go ahead and write in plus and plus. Now I need two numbers to multiply together to give me 3, but at the same time in the middle I get 5x. Well, 3, there's only one way to get it, 3 times 1. Now I need to figure out whether my 3 goes here or my 3 goes here. Well, if I put it here, that would be 3x plus 2x, which is 5x, what I want. If I put it over here, that would be 3 times 2, 6x, plus x, which is 7x, not what I want. So my 3 goes here and my 1 goes here. So now I factored this. Now it says find the remaining factors. Now I've got all of the factors. F of x equals to, we already know that these two were factors from the original problem. X minus 2 and x plus 3. And now that I've completely divided the rest of it out, factored the rest of it out, these are my other two factors, 2x plus 3 and x plus 1. Find the remaining factors. These two are the remaining factors because that's the factorization of what was left when I divided these two into it, right? So now these are my full factors of the original function, all right? So hopefully that ties kind of everything together for what you're doing. Anytime you divide a factor into a polynomial, if you get no remainder, then that is a factor. So by dividing this into that, we know the first one's a factor. By dividing this into the result, we know it's a factor, right? And so we know those two are factors, and whatever's left factors out into these two, so those are your two remaining factors. All right? So take that into with you and keep everything that we've kind of talked about in mind when you go in and start looking at your quiz.